Well, good morning and welcome to seminar. I won't make Brian totally introduce himself, but he's the chair of the seminar committee, and kind of his right hand since we don't have a seminar committee anymore. So we make him do all the work, and we're going to make him talk today too. But I know Brian from LSU. I was a postdoc when he was a grad student, and he had a whole bunch of tree cores turned blue. So we ended up working together trying to figure out how to subtract the blue from the NIR reflected so he could figure out his PhD work. But anyway, we both ended up here at Auburn. Now he went through industry on his way here, but he's going to talk about some of his work that I'm also involved in, so some joint work as well. And data I haven't seen yet, so I'm excited to see this because he wouldn't tell me the other day. He said I had to come to seminar. So with that, Brian, I'll go ahead and turn it over to you and let you talk about your work.
Okay, thank you. Yeah, this is a highly collaborative discussion, so I'm going through a pipeline of a lot of the work I'm doing across campus and within the school. So hopefully I don't get something that I'm not completely familiar with. I tried to pick the things I could understand to put up here. So a little bit of my background. I worked in international paper in the wood quality group, and so they have a genetics program, silviculture folks, and we actually did NIR really before I saw it being published in the literature. We were doing it there to characterize our pine trees across the South for lower lignin reduction. That was back when international paper had a lot of trees all over the South, and so they could dial in their chemistry with the idea that it would save a lot of money for their pulp mills. So I can talk about that now because I see an international paper person in the room, but you know, they no longer have all of that technology and everything. So, and then after doing my PhD, I went to work for Louisiana Pacific, and there I did something completely different. We did new product development. Oriented strand board at the time, they were the #1 producer of oriented strand board, and we did a lot of adhesive replacement, trying to find cheaper adhesive, ways to make the adhesive cheaper, but also new product development. And that was one of the real reason I came to Auburn was because I wanted to come to academia, but it didn't hurt that they canceled the R&D program there for Louisiana Pacific. So that made me jump ship a little bit sooner. But I remember during my interview, I was talking about green, and I can't remember who. Somebody says, somebody mentioned about, I probably was more interested in money than being green. And, I would say that was a fair statement considering an industry. You always have to be on the positive end of things. If you're not, you're probably going to be out of a job. So I would say that was an accurate statement. But going green usually couples being cheaper as well when you're in industry. So I try to combine these two diverse backgrounds. I always like tackling new things. For my undergrad, I actually did forest product marketing. And then I punished myself and went to wood engineering at Virginia Tech. It was one of the top engineering programs. And then I tackled wood chemometrics for my PhD, so I kept going in the reverse direction. And so sometimes that can be tough and intimidating, but it helps me to communicate with a lot of folks. So international paper, we were interested in plantation forestry, trying to, you're harvesting trees at a younger age, and so the stiffness is lower. So one of the key things we were interested in was how to counter that strength and stiffness while also maintaining gains, because through genetics, when you gain one thing, if you start selecting for another thing, you're probably going to lose the thing you gained. And so if you start selecting too many traits, it's hard to maintain other traits. One of the things that I like to talk about, and I talk about in my class, and this usually creates controversy, is I consider shifting power to the landowner. I think that that the future is not going to be the same as the past. So this is a real issue, I think. In the past, the landowner really didn't get paid for the quality of the things they grew because the sawmill could sort out the stiff from material through the older growth stuff, and then the younger stuff that came through, they could sort out. So they had machines that could sort out lumber based on stiffness, and so the landowner didn't get paid for growing things longer. And I'm not saying that it's going to happen anytime sooner today, but I do think that the landowner is going to be different in the future because if we don't have a way to measure quality. So how can you pay for quality if you can't measure it? So that's an issue. I think you can't go to a tree and measure the stiffness right now. And if we run out of older growth stuff, I think that the leverage will move to the landowner. So I think moving into the future, things can be different. Another thing that could be different is what if we start making oriented strand lumber, composites? Then do we need to make a 2x10? And that's something I challenged the students this morning. I told the undergrad students, I said, there's two scenarios. We could continue to make lumber, which might happen, or we could shift towards making wood composites in the future, and that might happen. And I don't know which direction we're going to go, but if we go into the direction of making more wood composites, then maybe instead of cutting a 2x10 out of a tree, maybe we're more interested in dry weight, because that's what's more important for the composite. So the future depends on what decisions, and I can't predict the future, so it's hard to exactly say what's important, but those are some of the issues I talk about to the students. One of the things I want to talk about from the wood composites is I've been working with folks across campus, Dr. Lamette All, with epoxy adhesives, and it's currently not used for structural composites. And so what I'm going to do today is I'm going to go through a pipeline that sort of combines these experiences and talk about how I'm working along the distribution chain to create a wood composite. And I tend to focus on oriented strand board, but looking all the way back to the Seedling and moving forward and linking it all together. And so I recently started working with Dr. Innebeck with their cooperative, and we had a visiting scholar from China, and he wanted to actually measure the chemistry, the sugars of the tree, and see how it relates to freezing the tree. And so it was like I told Dr. Innebeck, I said, well, this would be a good project to work on your area. And so I put him on this project. He was an associate professor. It slips me which university he's from, but he worked on this project. And so the idea was the problem or the issue that they have is freezing temperatures. They have seedlings, and when they plant them into the containers and there's a freeze, it takes a week or two for people to see this damage, and they've already sold this seedling. And so the idea would be, could we use near-infrared spectroscopy, which is an analytical tool to identify this if the seedling has been frozen. So that way, maybe you don't sell it to the customer because you can identify it the next day. And so that's the idea of what we were working on with this project. And so the mechanisms, when I look into the literature, the mechanisms are not very well understood. So there's an opportunity from an academic perspective to look and see how that chemistry changes as that seedling freezes. And then the other thing that I would like to point out, and maybe this is maybe it's not that relevant, or maybe it's highly relevant, but the survival of the fittest. If we're going to select trees based on freeze tolerance, does that shift what we're planting into the field? I don't know. I'm not a genetics person, but it's sort of making a decision about what's available down the road. And so, does that change any of the other traits? I don't know. So NIR is really, NIR, this is the NIR machine that we have, and it measures the absorbance of light across different wavelengths. And so, and in this particular graph, you can see these are different freeze temperatures. So this is from the data for the seedlings. But more often than not, when you see this graph, you see nothing. It's hard to see anything. And so what I did, my PhD, I focused on my area on multivariate statistics with the complementary and with chemistry. And so I usually have to collaborate with folks that are with chemists that can help me connect the dots sometimes. But But the multivariate analysis part I can do really well at. And so basically what we do is we apply multivariate statistics and we tease out information from the spectra here, and things that you can't see by eye, you can tease out into models. And these models can be very important because sometimes the model that looks really good to predict something in a lab, maybe it doesn't work well in the future, even though it had the best R-square, for example. So this is just the experimental design for that particular study. So basically there was one freeze damage where he put it in minus 15 degrees C, and he did different weeks of time. So this is some of the data that he got where he looked at some of the sugars, fructose, galactose, glucose, and he looked at how those sugars changed with different temperatures. And so that top row is whole seedlings. The second row is leaf, what he calls leaf, which is leaf, but needles, I guess I would normally call it needles. And you got stem is your third row, and you look at roots as the fourth row. And what he found was that the seedling, that the freezing temperatures appeared to change the chemistry of all of the different tissues. And so in order for NIR to work, instead of just showing that it can magically separate out something, it'd be nice to understand that its relationship to the chemistry. So these are some of the predictions that he was able to do with the different sugars, and so you can see that we can predict the change in sugars with the different treatments. So basically these sugars are changing during the freeze, and so we got a first slice at understanding how things are changing as it freezes. I think there's a lot more work that needs to be done, and I wish that he was here to dive into the details. So I guess in summary, what we're thinking is we're thinking that we can definitely use NIR to predict whether a seedling was actually frozen, whether there was damage. And so in other words, in a couple of weeks, is it going to be something that the customer is going to complain about? So we think there's good potential if it can predict the change in the chemistry the day after, then it should be able to predict the freeze damage within a week or two. So that's sort of the idea there, was instead of just doing some statistical study where you separate it out, and NIR can separate out to ones that were frozen and ones that weren't frozen, we tried to dig in a little deeper to figure out what's changing with the chemistry. So it looks promising. So then I also work with Dr. Eckhart and her group over in the Forest Health Cooperative, and I took this picture off of one of her publications, different leptographium, and I was going to attempt to memorize what each one was, and I didn't do it, but I do have the information. So the issue there is that there's been pine decline, or there's been trees that are unhealthy, and so she had a group of companies that got organized, and please correct me if I fudge up anything, but group of companies organized, and they said that they had forest health issues, and so they started this forest health co-op, and then the genetics folks gets involved, and they're the natural solution is let's breed for trees that have better genetics towards forest health. And so one of the things that I pointed out to that group is, what if you pick a tree that's good in forest health, but then the stiffness is lower? You just traded one problem perhaps for another problem. And so one of the things that I've been working with Dr. Eckhart's group is to make sure that we can at least maintain the stiffness for a healthier tree, or a genetic family, but maybe get the best of both worlds and improve both of them. And so, on the forest products end of things, as I'm going to talk about on the next stage, there's another issue besides just forest health issues. There's the lower stiffness, and so I'll talk about that in a minute. The Southern Pine Inspection Bureau has downgraded the assumed stiffness of the lumber, and so there's issues there, both with forest health but also with lower stiffness in lumber. relative to 10, 20, 30 years ago. So we need reliable tools in order to characterize these things. And we're looking at NIR and the acoustics to, and I'd say we're looking at NIR for chemistry, and we also model the stiffness. And I like to highlight the word model. I'm going to show some data here why. Because really what we're doing is we're not calibrating NIR to measure stiffness, because NIR is more sensitive to chemistry. It's not sensitive to the stiffness. So I think it's important to understand that stiffness is what I call a secondary trait. So in other words, you're using the chemistry to predict stiffness. You're using the spectra that's sensitive to the chemistry to indirectly predict stiffness. And so one of the things I always get on my soapbox with my students, and I always use genetics as an example, and I might have the smoking gun on the next slide, is what if this particular family, what if the relationship between the chemistry and the stiffness is different? So if you're not really measuring stiffness with NIR, for example, the model says the stiffness goes up or down, but what if the relationship between the chemistry and the stiffness is different for that family? Then your model's not going to work. So it's important to understand when you're modeling something versus when you're calibrating something. And a lot of times when you look into the literature, people try to make titles fancy, and in the process it makes it look like you're measuring something. Like elucidate, that's a really good one. If you really want to get a publication published, use the word elucidate in your title. People really like that. This is a site that we looked at with different families, and the codes down at the bottom are coded so that I don't know what's going on. Probably because the company thinks I'm going to tell another company, which I know they don't think that. But, and so you can see here with the families, and what we did was we compared NIR to acoustics. And so the NIR model, so we took the spectrum, we did a partial least squares regression model that we applied to it, and we predicted from the spectrum the stiffness. And you can see that the NIR, for all of the families, except for one, does a good job. And this is at a Georgia site. There's one family where the NIR does not do a good job. So if I was using NIR to screen families, I would miss this. So the acoustics does a better, is able to identify what the NIR was able to miss. So this is genetic family A33, and this was the Georgia site. So we had another site that was a Florida site with the same families, and this was a block design, so it had the exact same families randomly distributed in blocks at each site. Really, I argue you have two blocks. You have the blocks within the site, and you have the two different geographic locations. And when I went to the next site, Florida, same families, look at A33, same thing. So there's something about this family, A33, that the NIR model, which is really just sensitive to chemistry, is not picking up. And perhaps it could be microfibril angle, which is the angle of the cellulose. So I've always felt like NIR isn't really seeing microfibril angle, it's just seeing correlations between wood chemistry and microfibril angle. The microfibril angle, just to give you a rough idea of what that means, because there's a lot of foresters in here, I explain to my students, if I'm pulling this pin, I pull it parallel to the axis, it's pretty strong or stiff in tension. But if I take the pin and I angle it, but I still try to pull it in a plane at some angle to that pin, I asked them which one's stronger this morning. They answered this correctly, that the one parallel to the pin should be stronger. So if the pin is parallel to the force, it should be stronger, it should be stiffer, and that's the case. And so the microfibril angle, I've always been suspicious that NIR isn't really seeing the microfibril angle because there's a debate, I guess, that goes on about that. One of the things that we do here is we grind the wood up, so that makes it even more challenging because it definitely can't see the microfibril angle if it's ground up into a powder. So because one powder or one particle is going to be completely different than another particle. So there's something going on with this particular family. So figuring out what's going on with that family, I think the companies might be interested in that. So that's the new data that I told Dr. Eckhart that I had. So So this was my explanation of the microfibril angle. And this is where we're able to see the microfibril angle in our lab using a technique that Gary Peter from Florida developed. I actually developed it when I was at IP2, but I couldn't publish, so he gets credit I don't. One of the reasons I came back to academia, so I'm telling my wife that I told her it's because I was going to get kicked out of my job. She believed me. So one of the things NIR really, it's debatable whether it really sees microfibril angle. It probably sees correlations of cellulose and lysosis and lignin. It also is sensitive to wind density because, as you might imagine, if you have more material there, it's going to absorb light. And so it could be associated with those things which co-vary with the microfibril angle. So I would say that the moral of the story is that if you're going to do genetics work, NIR could be very helpful for genetics, but you want to understand the covariance matrix or the correlation between all of the traits. And what does NIR really see? And then for the genetics part, for example, is that microfibril angle, is it related to an environmental effect or a genetic effect? So is that cellulose or lignin to the microfibril angle relationship, is that more driven by genetics or is it more driven by the environment? Because if I create a calibration equation that's more influenced by the environment, like somebody's adding fertilizer, but then I take it over here and I apply it to a genetic study, it's going to look pretty impressive, but it might not be good data. So that's something that you have to consider, is what are those underlying relationships when you're doing modeling. So we've already started getting into wood quality, and I mentioned earlier the new design values. So in 2013, the Southern Pine Inspection Bureau lowered the design values for lumber. And what I mean by that is they lowered the assumed stiffness and the assumed strength of a piece of lumber. So if you look at a piece of lumber and it has a certain knot size, you assume it, the engineers assume it has a certain strength and a certain stiffness. So that way when they go to their house, they can build the house to resist a load that they expect to see based on the snow and the wind loads and whatnot. And so in 2013, SPIB did they enacted, they actually did the study a few years before. They tested a bunch of pieces of lumber and they concluded that the strength and the stiffness has lowered. And just to clarify what the difference is between strength and stiffness, if I step on a piece of lumber and then I step off, that amount that it bends is the stiffness. And when I step off, it comes back to its original position. That's stiffness. It doesn't break. Strength is when it breaks. So that's the difference between strength and stiffness. And so the new design values has really caught the attention and maybe the debate, because maybe the landowner that has grown trees are now under more pressure because maybe they're getting some of the blame for why is this quality lower? So typically between the processing folks and the landowner folks, sometimes you get maybe some finger pointing that goes on between both of them. And I think it's just the way things are. I don't think anybody's to blame. So why is this important? In our state, we used to be number one in all categories. Some categories were number two. Forest products industry is still the second largest industry in the state. And one thing, when I worked at Louisiana Pacific, we wanted to put an orange strand lumber plant in the south because it was cost effective more than the north. And our CEO really wanted to do it, but in the end we didn't do it. And the reason we didn't put a plant into the south was because the stiffness of our raw material is too low. Now keep in mind, they wanted to use pulpwood type material, so the pulpwood is going to be lower stiffness anyway. So that issue could be outside of the whole argument about SPIB lowering the values, but it's still an important thing to understand. I was at a meeting and I met a committee member from the SPIB, so that they had a committee, and there was a sawmill owner that was part of the SPIB committee, and he gave a presentation, and said, we survived this downgrade. In other words, we're still business as usual, things are going well, doesn't seem to be impacting too much. But he says if we have another downgrade, it can be very disastrous. So Charles will appreciate me showing this. Gives me well, it doesn't really give me a break because I usually talk through it. So this is the acoustic system, and you can buy this system right off of the shelf. But currently, industry is not really using this acoustics technology. So, but what this technology does is it just puts a sound wave through the tree. And Charles is going probably slower here for demonstration purposes. He can go a little faster than this, but still it takes, I don't know, what, a couple of minutes to do. So the first issue you get with somebody doing a timber cruise is how can I justify going around measuring 20, 30 trees? So that's something that has to be considered, is how much time this thing takes. But what we do is we put it in, and he's measuring out, I guess, roughly 3 meters. Is that right? 1.2 meters, 3 feet. I meant to say 3 feet. Yeah, not 3 meters, but 3 feet. We're getting my units confused. So he's trying to put these things in. He'll send a sound wave. And then the immediate argument that you get into is the sound wave going along the edge of the tree, or is it going through the center of the tree? Because if it goes sort of in an arch, then if you have a smaller diameter and you have more of the weak juvenile wood, then it might influence the data. And so I think there's a lot of questions with this technology. How do you get around some of these issues? But anyway, these are some of the things that we're working on. So then what he does is he taps this thing, and then it sends a sound wave. So you can hear it sending the sound wave up the tree. So that's just an example of the acoustics work. And one of the things that I always try to teach the students is to ask why and not to assume. So for example, if you go out and you look into the literature, acoustics is great. Same thing with NIR, measuring microfibrillating angle is great, let's do it. And so I always challenge the students, don't pay attention to what everybody's saying, let's look into it ourselves. And so one of the questions that I have with this thing, that Charles also had, is what if acoustics is more sensitive like density of the wood, but then maybe the real piece of stick of wood is more sensitive to microfibrillating angle? Because maybe juvenile wood, the younger wood, is not the same as older wood, more mature wood. So we need to really do a study where we're in experimental design, where we're answering the question, does acoustics see the same thing as when you're breaking a stick of wood? Put another way, if you break a stick of wood, does your chemistry and your anatomy have the same influence on breaking a stick of wood and measuring the stiffness from that on the right side versus those same anatomy and chemistry? How does it influence the acoustic signal? Because we're using the acoustic signal to estimate the stiffness. And I was actually pleasantly surprised with this because you get essentially the same results. When you're breaking a stick of wood, you get the same statistical significance in the multivariate world. So we use multiple linear regression to measure the p-values. And what we found is if you look at hemicellulose, same p-value. If you look at microfibrillating angle, almost the same p-value. Oven dry weight, same p-value. Lignin, both significant with the acoustics of lignin being a little bit more, I'm sorry, that's cellulose at the top. Lignin was a little bit different. So you're not ever going to get exactly the same significance, but these things were quite similar. And so what this essentially says is that acoustics is sensitive to microfibrillating angle. And it's not just some correlation between lignin and microfibrillating angle or cellulose and microfibrillating angle. So it really does see microfibrillating angle. And it does see the suite of traits at the same magnitude as what you see here. Then the other thing we found out through the model is it makes sense in terms of how it explains things. Like we would expect cellulose to transmit sound quickly, while we would expect lignin to absorb sound. And that's what the model demonstrated. So a lot of times, instead of looking at the R-squared of the model, it's better to go in and look at the interpretation. So hopefully the idea here is that we can work towards separating these trees toward added value. Now this is some of the NIR work we're doing where we're measuring the wood chemistry. And when I was in industry, what we would do is we had a set standard. We would grind, we would actually take out the extractives of the samples first. But here we don't take out the extractives because sometimes I'd like to know what the extractives content is. So we've collaborated, Dr. Fan and collaborated with Dr. Eckhart, and we've collaborated with NC State and Tennessee and Biosystems Engineering. So we've got different species that we've looked at, and what we've done is we've created a process where we grind a 4D mesh, and then we put it into the NIR and we measure it. So that way we have a set standard as to how we do it. Because a lot of people like to do the solid wood, but the solid wood, depending on whether you're in the radial or the tangential phase, it will change the way the spectra looks, and it adds a lot of noise. So by grinding to a specific mesh, we're able to get better models. And so these are some examples of some models that we've developed that we could use to predict the chemistry. So like for example, we've taken this model from Southern Pine, and we've also taken other models from loblolly, specifically loblolly, and we've dropped it to those 14 families with Dr. Eckhart's co-op for loblolly pine. So then on what we do is we're starting to, I call it reconversion, but we're making some bio-based adhesives. So now I'm working with people across campus. And so I work with Biosystems Engineering, Sushil Adhikari. He does pyrolysis, and then we also do liquefaction. Pyrolysis is where you heat with the abscess of temperature and you convert the wood into a ball. And then that can be used for fuels. But what we're trying to do is figure out how to, instead of use it for fuels, see if we can use it as a feedstock for adhesives. So on the left side is his pyrolysis lab, and on the right side is a reactor, a par reactor, where we do the liquefaction. So the liquefaction is where we had to solve it to the wood, and we heat it at high pressure and temperature, and we take out the oxygen, or you can, and then we can convert it to a similar looking ball, but chemically it turns into something very different. They look the same, but they can be quite different in their chemistry. So what are some of the issues that we've discovered with this? These are well-known issues in the literature, so it's not like we really discovered this. But one of the issues with ball is that it will polymerize as it sits. So if a manufacturer has a bucket of balls, so to speak, if you let it sit there for time, it'll slowly react and polymerize, and it will thicken. So the viscosity will increase, and so it's not stable, but it's dynamic, and so that can be a challenge, because if you're going to do the adhesive, if you're going to use ball as a feedstock for adhesives, you want something that's consistent. And that's another challenge, is it's not consistent. When I started working with Dr. All on the next section when we do adhesives, she used to get very frustrated because she's like, what's really going on here? Because there's hundreds of compounds in this ball, and I don't think we really know what's going on. But anyway, we try to figure out what these reactions are that are not well understood. This is some of usage for graduate students' work, and where we used liquefaction and we created a ball. And what we were interested in is we were interested in the OH, the hydroxyl groups, because when you react the ball with the adhesive likes to react in these OH groups. And so the more H groups you have, the better you are. And so this is what we have found is when we do different temperatures for liquefaction, we get different hydroxyl groups, and when we use PNMR, we can actually separate the hydroxyl groups, whether they're aliphatic, phenolic, or acetic. And so we can look at where the OH groups are sort of coming from. And this is where Tom can jump in and add some value to this, because I had to dig into the literature. I tried to come up with a reaction I thought that was going on. If you increase your temperatures, you start to see more and more phenolics. And so one of the things I did through the literature, and I looked at the beta 4 position of lignin, and that's like a really common type of link that you get. And as you increase the temperature, you go from step 1 to step 4. And so as you go from you increase your temperature, you go to step 2. You increase your temperature, you go to step 3. And eventually when you get to step 4, you end up with a phenolic. And so as you increase your temperatures, lo and behold, you end up with more phenolics. So that's sort of my hypothesis about what's going on. But keep in mind, this is a very simplified hypothesis because there's hundreds of chemical compounds in biol. And but this is what I come up with. So then we move on to adhesives, and I work with Dr. Maria Auld over in Polymer and Fiber, and she just published one paper, and quite frankly, I'd have to dig really into it and learn a lot of things to understand what was going on, so I pulled some of her easier data out. This is an example of an epoxy adhesive that she pulled out that she has made with biol. So what she's done here is she just takes the biol and reacts it with the epoxy. And so what are some of the opportunities with epoxy? It's one of the largest polymers used, but it's not used in wood that often. So, but on a global scale, there's a lot of volume that's produced. So there's an economic, opportunity there if you could make it work for wood. It's expensive though, so that's another reason why it's not used in wood. So there's sort of really two reasons why epoxies aren't used in wood. One is it's expensive, and two is that epoxy itself is very resistant to moisture, but when it bonds to wood and you throw it in water, it's not resistant to moisture, it tends to fall apart. But one of the advantages of biol is that it's hydrophobic, and so it can resist moisture, and so maybe there's some added benefit there. Another opportunity is that epoxies are formaldehyde-free. There's phenol formaldehyde and urea formaldehyde, and there's adhesives out there where people get upset over the word formaldehyde. And when you talk with folks, a lot of times the formaldehyde will react and it will cross-link, so it's tied up, so it's not a danger, but people perceive that it's a danger. And so companies are switching to non-formaldehyde adhesives, even though in some cases it might not be necessary. Perception doesn't always equal reality. But one of the issues, or several issues that we run into, is, like I said, the epoxy bond to wood will fall apart in water. There's different epoxy systems out there, but then also when we look at different biol, like if we take biol through liquefaction and we take biol through pyrolysis, the chemistries are very different, and so there's different reactions going on there. So on the surface, it looks the same, but you get different epoxy to biol ratios when you mix it together, whatever the optimal ratio is, optimal recipe, if you will. And so getting something consistent is going to be important. So this is where she made epoxidized some biol oil, and what she does is you want a lower bar here, so she added, I believe, the acetone. I didn't put up here, I believe it was acetone, yeah, I did put up there. So she added acetone to it and tried to make it fall apart. And so the lower bar is better. So those are some of the things that we're working on with her. And then we take the adhesive, and then we have a step in between the wood composite and the adhesive where we could reinforce the adhesive. And so we just hired a new faculty, Soledad Parisian, and she is a nanocellulose expert. So I looked into her literature. She's in Finland right now. She's not answering her emails right now in a timely manner. So I just took the liberty of grabbing a couple of her things from the literature and throwing it up here. So if you see anything wrong, it's probably my fault. So this was the table that she put together in her lit review. And basically what she's showing is that the nanocellulose down here at the bottom has better tensile strengths than most of these other things except for carbon nanotubes. So nanocellulose has some very good benefits. One of the weaknesses to nanocellulose And I hear all sorts of prices being thrown out there, so I don't really know how accurate that I know what I'm talking about, but I hear nanocellulose is $20 a pound. So that's one of the reasons, if it's $20 a pound, that's why nanocellulose probably isn't being utilized, because normally, to put that in perspective, MDI or epoxy was about $1.50 a pound. So unless you can use a little bit of amount of nanocellulose and get a huge gain in strength, then it might still be worth $20 a pound. But one of the issues that the industry sees is the aggregation of the cellulose. When you're trying to disperse this stuff into the composite, the cellulose it's attracted to each other, so you can't easily disperse it into the composite. And so those were some of the real issues. Is it's very strong, but how do you disperse this stuff? And so some interesting work that she's doing that I find very interesting is they're making nanocellulose out of pulp fibers, and those little arrows represent nanolignin particles. And so these fibers are covered with nanolignin particles. and in the paper, they say that this can help with dispersion because the lignin keeps the cellulose from aggregating. And so you can disperse the cellulose and hopefully have it equally dispersed within the composite instead of it bunching up in places. Another thing she found was those little nanoparticles, when you process it, you get a smoother surface on the right side from when you have the nanolignin on there versus if you don't. And that's where the lignin easily flows under a temperature, and so it can flow and redistribute itself and then attach the composite back. So this has applications towards packaging and other type of applications similar to that. That's sort of what she's working on. We've been working on sort of a similar thing in wood composites. And by similar thing, I mean we've been interested in just depositing cellulose, because we've also had that issue of cellulose likes to agglomerate. So here we're looking at just fibril cellulose, and the idea we came up with is always try to take the approach, how can we come up with a solution for industry? So I sort of work backwards. Like a lot of times when you're in academics, people will design the experiment and then they'll come to a conclusion. What we'll do a lot of times is we'll work backwards. We'll find what works. This didn't work, this didn't work, this didn't work. But then when we find something that works, then dive in and understand why did it work. And the reason that we go backwards is because we're trying to work in an environment that matches what the industry can use. And so what we did here was we just took, and this was paraffin wax. The industry doesn't use paraffin wax, but the idea here is they use the slack wax, but they distribute the wax in the OSB. The wax is to help keep the moisture, to retard the moisture. And so we thought, well, if they're adding wax to OSB, then maybe you could use the wax as a carrier for the cellulose. And then the wax could keep the cellulose from bunching up against each other and agglomerating. And so what we did was we simply just created different ratios of wax to microcrystalline cellulose. And you see as you go from pure cellulose on the top left to right, you can see more and more wax being put on. Of course, the whole idea of putting cellulose in a composite is to increase the strength. So if you start putting wax around it, then the problem then you got a balancing act, because now the cellulose can't react with the polymer that you're putting in it. So you have to do sort of a balancing act, try to partially cover it, so that sort of you have elbows on it, so that it keeps the cellulose from touching each other, but there's exposed parts that can link between the polymer and the cellulose. And so that's sort of what we found, is that if we just put just enough coating on it, but leave some of the cellulose exposed, then you can see over there between the control and that 1% loading we get the highest value. And on the left side we have dry, and on the right side we have wet. So then finally with the wood composite, so we've done some work with ball, and maybe 4 or 5 years ago we looked at impregnating ball in the wood, and I'm sure this is no surprise to some folks in the room, is that it does a good job against resistant high humidities. So if you put ball in the wood, it helps the wood to retard that higher humidity for a short period of time. But if you dump it in water, the bottle will leach out because it hasn't linked to anything. So that's what that bottom graph shows. If we throw the wood in water, it has bottle into it, it will leach out into the water. And so that was about the time that I met Dr. Auld across campus to work on the epoxy adhesives, because we was trying to figure out a way of fixing the bottle to the wood cell wall. So I guess we all think that what we do is novel. I think this is really novel from a practical perspective, but I keep submitting this NSF and it keeps getting rejected, so maybe it's not as great as I think it is. But I think this is novel because I told you earlier that when you test epoxy, you glue two pieces of wood together with epoxy and you throw it in water, it falls apart. So you can see that here, you can see the strength reduced. But if we mix enough ball oil in there, and you have to put enough ball oil into the epoxy to do two things. One, to react with the epoxy, but have a little bit left over to react with the wood substrate. And the reason you want to react with the wood substrate is because the ball oil is hydrophobic. And so if it can tie up sites, through different ways, which is beyond this discussion, it can maybe make the wood more moisture resistant. And so that's what we found, is we found that the epoxy could perform well with the ball oil. So what we think is going on is that the ball oil keeps the wood from shrinking and swelling when you dump it into the water, so there's less forces on the adhesive bond line. So then it holds together. So that's sort of, so what I've done here is I've connected across campus, working, and we work with other people too. I didn't include everybody. So I've been looking around the room to make sure that nobody's here that I haven't missed. So we've been working with other people across campus, but I wanted to pick a theme where we were going across the distribution chain from beginning to end. And so moving forward into the future, I just wanted to remind folks and let some of the folks that know we're starting a new undergraduate curriculum, and we've taken advantage of people across campus. And so it's been a lot easier than I thought it would be. It's still a challenge to pull people together, but we've got people from business and College of Architecture and engineering and agriculture and then forestry. And so one of the reasons that it's been easier than I thought it would be is because the people the team that we've put together is the same team I work with for this research that I showed you. So when you work with these people for almost a decade, it makes things a lot easier than if you just approach people, let's put something together. So this is very similar to the research that I showed, where we have biomass and logistics, we have products, and then we have a business component and a sustainability component. And I did mention earlier the debate between whether something's green or whether it's just saving money. So that covers the sustainability and the business part of my research. And these are the different units that are involved, which I mentioned a second ago. And so with that concludes my presentation, and I'm open for questions, fist fights. I know I threw a lot of different things at different angles since I'm working with a lot of different people, so. No questions? Okay. Well, thank you for coming.